Math is scary. Learning math is like learning a foreign language, only there's math in it. And learning calculus is especially scary because what calculus does is it takes all of the concepts that you've spent mind-numbing years in math class learning and then changes all of the rules on you. Like, okay. You can find the slope of this linear line using rise over run, and it's pretty easy. But then when you show up in a calculus class, they want you to find the slope of a curved line, and that's terrifying. Although it's actually relatively simple. You could find the slope at a point using successive approximations. Here's the equations for that. And you could find the slope anywhere on the line by finding the derivative. And here's some derivative rules that you can use to help you find that. And hey, get back here. We have math to do. Whoa, stay there. I promise to make this a lot less scary for the rest of the video. Let's just zoom in at this graph at around negative 1.5. And I'm just going to ask you to just guess what the slope could be. And your answer would probably be something like around 2. And you'd be right, it is around 2. All that complicated, scary math language was really just doing the same thing you just did. It just did it more accurately. My point is, calculus looks intimidating and scary because all these weird letters, but what all of these equations are doing is actually fairly intuitive. But why do we even need those numbers if it's so intuitive and straightforward? Well, for one, the capitalist oppressors need some way to crush the souls of the youth, and math tests do a really good job of that. But also, it's so much more accurate. This number is way more precise than around 2. And that accuracy can matter. Oh, why did I do this bit? This was a very poor decision. So traditionally, people tend to either use population growth or acceleration and deceleration while driving to help explain derivatives. I'm not going to use population growth because, well, I don't want to. And I'm not going to use acceleration and deceleration while driving because I'm going to make a joke about drinking alcohol a little later in the video. And you should never take driving derivatives drunk. So instead, let's talk about insulin. Insulin is the name of a tiny dragon that lives inside of your body and hoards sugar. The dragon can only be defeated by Bilbo Baggins, the hormone. Insulin is a hormone. Beta cells in your pancreas secrete insulin into the bloodstream, where it then goes and gathers up any glucose floating around and stores it for future use. So kind of like a dragon. This is a graph of insulin secretion rates, or how much insulin is going out of the beta cells after someone's had a bunch of glucose shoved into their bloodstream, like they took a shot of pure glucose. This is the joke about drinking I was talking about earlier. Whew, that's some good glucose. So you've probably heard of diabetes, which is a type of disease that messes with insulin in some way. Type 1 diabetes messes with beta cells, so they can't secrete enough insulin to store the glucose that's in the bloodstream. Let's take a look at a graph of insulin secretion rate in a type 1 diabetic. There's an obvious difference between this and the previous graph. The type 1 diabetic obviously secretes much less insulin, and you can look at any specific point in time and tell me how much less. But what can you tell me about the change in the insulin secretion rate over time? You can tell me that the normal person secretes more at any given time, and that the first part of the graph goes up more, but then it also goes down a lot more. But that's not very accurate, is it? Let's take a derivative of both of these graphs and see what happens. Now, what this graph shows us is the rate of the insulin secretion rate. That's confusing. Let me see if I can explain that better. So what the previous graph showed us was how much insulin was being secreted every minute by the beta cells. And what this graph shows us is the rate of that number. So whenever it's positive, that means more insulin is being secreted than was being secreted a minute ago. And when it's negative, that means less insulin is being secreted than was being secreted a minute ago. That's what rate of insulin secretion rate means. And that's what derivatives show us in this case. So now, let's look at those derivatives. Now that's a dramatic difference. Notice how in the non-diabetic person, the change in insulin secretion rate is very positive and then very negative and then returns to a positive state and kind of levels out over time. In the type 1 diabetic person, it's positive and then it goes negative, then it never returns to a positive state. And in general, all the numbers are much smaller than at corresponding points in the normal person's graph. This shows us that beta cells are much less responsive in a type 1 diabetic person, and we can quantify that change in responsiveness. In short, taking the derivative here shows us something that we kind of already knew from looking at the original graphs, but it gives us a way to communicate that knowledge more precisely. It's not particularly shocking, but it is useful, and it's nice to be able to talk about these kinds of things accurately without just looking at a graph and going, around 2. How many of those have you had? Around 2? Now let's look at something really cool. So they did a study where they tracked insulin response in type 1 diabetics who were newly diagnosed over the course of about 2 years. And they looked to see how insulin secretion rate changed in response to an influx of glucose over that time. So let's take a look at all of those graphs. Again, we can see some pretty obvious conclusions. None of these are as responsive as the normal person, and the longer they've been diagnosed with the disease, the less responsive the beta cells seem to be, and the less insulin is secreted. Now let's take a look at the derivatives. So what we can clearly see here is how the change in insulin secretion rate gets less and less the more time someone has type 1 diabetes. Again, that's not something you couldn't have gotten from the earlier graphs, but these graphs show you that directly and independent of any other variables. And it lets you quantify those differences in a way that can be easily explained to someone else. So what's the point of all of this? Yeah, I changed backgrounds. Calculus isn't scary. It's a tool. And when you're using that tool in the real world, the results will make perfect sense. But using calculus means you can be more clear and precise in how you talk about and describe changes over time. Knowing about insulin secretion rate is important, and knowing about the rate of insulin secretion rate is also important, and together they give a better, more precise picture of the changes happening in beta cells in someone with type 1 diabetes. Speaking the language of calculus is hard. That's why we take classes about it, but the concepts themselves are not the hard part. Just like learning how to speak a foreign language is difficult, but a picture book written in a foreign language isn't particularly difficult to grasp. So please, use math when you need to, and use calculus. It can help you enrich your understanding of the world and communicate in a more clear and precise way. And if you're still scared of all of these crazy letters, well, that's what the glucose is for. Where is it? And remember, don't take driving derivatives drunk.